Good morning. Welcome to Krishna's classroom. We continue with our discourses on Riemann integration. This is the sixth in the series, and we recall what we did last time. We introduced a theorem which gives an equivalence to the criteria of Riemann integrability. This was a very useful one because it just involves computing LPF and UPF for a given function f rather than going to the upper integral and lower integral. And we use this theorem, or we apply this theorem to show that certain functions are Riemann integrable. In this regard, we already explored one of them, namely that all monotonically increasing functions are Riemann integral. This we proved using the characterization of Riemann integration. That gives a wide class of functions which are Riemann integrable. It's a huge class of functions that you have. Now the second one, we want to explore this further, and if possible, we would like to get a characterization of all Riemann integrable functions. Before that, we explore this further, and then we look at another class of functions which you often deal with, namely all continuous functions. So the question that you ask is, are continuous functions on the interval AB Riemann integrable? So let us see this. So we assume f from AB to R, the real valued function. We assume f is continuous. Then and this is what we expect, or rather we would like, rather than expectation. So we would like to have these functions Riemann integral. So I put a question mark for the time being. Is f Riemann integrable? So once we prove this, then you see that the entire class of continuous functions on the interval AB, which is a very interesting class of functions in analysis, namely we designate it using the symbol CAB. All functions in CAB are Riemann integral. So these are the class of continuous functions on the interval A. Let us see how we can prove this. So f belonging to CAB, f is Riemann integral. Short R5. Let me see how we prove this. First of all, we make an observation, because the strategy that we are going to use is again this. Given epsilon positive, find a partition AB Is it possible to find such a partition? Now this is what we are going to examine. And if we can prove this, then it implies F is Riemann integrable by the characterization theorem. So let us see how we can work on this. Now the first thing that you observe is, our assumption is that F is a continuous function. So it is on the compact interval AB. And say, I'm not assuming F is positive or anything, or you can do one, you can even do this. Okay. Something like this. So this is a continuous function. So this is y equal to, assume it is continuous. Now the first thing that you observe is that, of course, F is bounded, because we are working on a closed bounded interval, therefore F is bounded. This is the first inference that you make. The second inference that you make is the following. F is not only continuous, but F is also uniformly continuous. Second inference is F is uniformly, use a closed bounded interval. What is the meaning of this? The meaning or the implication of this is that given epsilon positive, uniform continuity is a global phenomenon. Epsilon positive, there exists delta positive, delta independent of x belonging to AB, such that mod x minus y less than delta, or xy belonging to AB, comma, mod x minus y less than delta implies f of x minus f of y less than. Since this is a compact interval, or what you call a closed bounded interval, and f is a continuous function, we can prove that it is uniformly continuous. What does this say? It says, given epsilon positive, there exists a delta. If you are talking about local continuity, then you know for each point you can choose a delta. Delta would in general depend on both epsilon and x naught. Okay? Now what we say is that universally for all x on the interval AB, given an epsilon, you can choose a delta. That delta depends only on epsilon and not on the points in A. This is what you get. Okay? So we have set up a, starting with an epsilon, we have got a delta. Now what one does is, what we are searching for, we are searching for a partition P such that UPF minus NPF is less than epsilon. Okay, let us be, choose a simple partition. Like, so let P be a partition, what you call a regular partition, x naught A equal to x naught less than x1, and we choose the distance between xi minus xi minus 1, we fix this to be equal to, this is the length or the distance, equal to b minus a divided by a. That means all these points are equidistant on the interval. There are n intervals and each interval has length b minus a by n. And their union is equal to ab, but they intersect is at close to 1 point. Okay. So you can actually list it out. Okay, it's not difficult at all. Okay. Now what one can do is you can play around with this n, and given epsilon we have already got a delta, and therefore what do? We make this less than delta. So set that is the delta that we have chosen for the corresponding epsilon. So already delta is there, the delta coming from the uniform continuity. Okay. Now what do we do? We write down the difference of upper sum and lower sum. So let us write u minus L. This is actually equal to sigma my into where mi is the least upper bound of f on the interval xi minus 1 xi, and small mi is the greatest lower bound of f on the interval xi minus 1 to xi. Both these numbers exist. Okay, so that is it. So therefore, what can you say about mi minus mi? Now since xi minus xi minus 1 is less than delta, we have mi less than epsilon. What is mi? Mi is for some x, it is fx, for some y, small mi is fy, and that is less than epsilon. This is consequence of UPF LPF is then epsilon into sigma. This is equal to epsilon into. So it's a multiple of epsilon multiplied by the number b minus a. B minus a is fixed as far as the interval is concerned, and this shows that you can make this arbitrarily small by choosing a partition. Okay. So if you are very particular and to get this epsilon, you start with an epsilon 1. Epsilon equal to epsilon 1 divided by b minus. Then corresponding to epsilon 1, you have a delta. Say delta 1. And then you repeat the argument with, choose n such that b minus a by n is less than delta 1 and so on. And you can make this equal to. That is just usually what the analysts play around with. But this result tells you that there is a P such that UPF and LPF can be made as small as you want by choosing the partition. So this is possible. Therefore, all continuous functions on the interval AB are now Riemann integrable. So we have got plenty of functions which are Riemann integrable. Now here again, one thing that you should observe is that we have made use of the characterization of Riemann integrability in terms of U and N. Because it is easy to compute this rather than going to the limits or what you call the infimum, supremum, and then checking them whether they are equal or not. And that has been reduced to this one. So it's a very handy rule that you can apply. So what I want to assert is that now we have plenty of functions which are Riemann integrable. In fact, what we would like to have is a theorem which says that f is Riemann integrable if and only if a certain condition holds. Okay? So that's what we are looking at. But before that, we'll make some explorations and look at some properties of Riemann integration and so on. So look at some examples. Let me just take out this. So I think I can remove the question mark here. We have proved that it is Riemann. So all monotone functions are Riemann integrable, and in fact I have written here monotonically increasing. You could as well do it for monotonically decreasing functions. Because if f is monotonically increasing, then minus f is monotonically decreasing. And if f is Riemann integrable, minus f is Riemann integrable, that I think we will be proving soon. So that once we see that, okay. Now we look at some examples and see how we get about working on these results. Let us look at some examples. Because in the first criteria, we imposed monotonicity. In the second criteria, we imposed continuity. So monotonicity does not imply the function is continuous. Here we have imposed continuity of the function. What we are seeing, suppose you have a finite set of discontinuity for the function on the interval A. Is that Riemann integrable? So this is the problem. So we examine some examples. The first example is we take fx to be equal to 1 for except x not equal to 1, 2. So we have defined the function in the following way. On the interval 0 to, you have 1 here, and then over here the function is defined as 1. Take this function to be equal to define the function to be equal to 1 over this interval, and at this point we define the function to be equal. We examine whether This is one of the simplest discontinuous functions that you can define. Is this Riemann integral? In this connection, in proving most of these theorems, you recall the following. You can give a partition. So we choose one partition P. P may not have 1 as a point in that. So what is that you can do? You can introduce 1 also into the set. So you can get a P1 where 1 belongs to P1. Okay. So it gives a partition. What happens to the criterion? You see that L, P, F, L, P1, F less than or equal to U, P1, F. Therefore, if the partition does not include 1, you can always get a refinement of P which includes 1. And then for that one, we try to compute the upper sum and the lower sum and get the difference. That is one. So any partition can be, without loss of generality, chosen as having the point of discontinuity in it. So that is no problem. But to analyze this one, what we do is the following. We compute, we choose an F. Assume F does not contain, assume Now let us compute U, P, F minus. See that as far as the other points are all concerned, they are here. So this is your xi minus 1, this is your xi. Okay? And in this interval, you see that the minimum of the function is equal to 1 and the maximum of the function is equal to 2. So what you get at all other places, the function is a constant function, therefore the difference f of the mi minus mi, capital Mi is equal to 1, small mi is equal to 1, this is 0, therefore this sum reduces to simply 2 minus 1 into xi minus 1. This one. Now how do you make this small? You can make this as small as you want by choosing xi and xi minus 1 sufficiently close. So choose the partition P such that xi minus 1 is less than that one gets UPF minus LPF is less than. So we have successfully got a partition of the interval 0 to 2 such that UPF minus LPF is less than epsilon, which implies F is Riemann integral.